All right, well, I'm going to start the stream. I'll start the review in about a minute once everything gets caught up, but I want to make sure everything's working good and that we're all here, or at least I'm here. Let's see, 6:29, so fast forward to like a few seconds if you're watching this in review. But looks like we're just about ready to go. All right, well, before I get going too much, I'm just going to point out that you're going to see me looking at the screen a lot, or at the camera, but over here to my left, to your right, are my monitors, so I'll be looking over here all the time to see what's going on, see if there's any questions on the chat, and I'll be looking over to my right, your left, because this is where I'll be writing stuff. So pretty sure everything's gonna be going pretty smoothly, but if not, let me know and I'll see what I can do to fix it. All right, so I'm gonna start officially. And so, like I said in the chat, I think you can read it still, but if you have questions, please use that to ask me questions. You could use the Remind app as well. But I just wanted to, let's see, to get my timer going. Okay, start. Nope, definitely don't want to do that. All right. I don't want to waste your time. So, the test. Today's Wednesday. The test is going to be Friday. It's going to be 3 parts. It'll be online. Almost every single part of it will be online. And the 3 parts are, as you can see here, distance time graphs, velocity time graphs, and the kinematics. So the kinematics we just quizzed on today, so you definitely want to go through that and see what you're missing, what you need to work on. But also definitely don't forget about the velocity time graphs. I know that quiz was challenging to a lot of people, so just definitely look at that and let me know if you have any questions tomorrow. For kinematics, the last one, that was obviously what we just took, and looks like my little mug there is getting in the way. But these are all on the equation sheet, and you will have access to an equation sheet. I'm going to give you one that's official. It's going to be fresh. It's not going to have your writing on it. It'll be laminated and everything. But you're going to have access to this equation sheet and also a 3x5 note card. Okay, so the 3x5 note card we can work on tomorrow in class. All right. What I'm basically going to do is just go through the review guide a little bit. And I'm definitely not going to go through every single one because I want to keep this to about a half hour or maybe 45 minutes, an hour at max. But I want to go through some of the things that might be challenging, things to just kind of watch out for. So, starting with the front page. First of all, I called this part Foundations because it doesn't really fit into any one category, but you do have to know these things. So definitely make sure you are just completely comfortable with the difference between speed and velocity, distance and displacement, just those ideas. All right, you're starting to see how velocity and specifically direction of the speed is starting to play a role, or acceleration because of negatives. That is going to not hit us so hard in this test, but is going to be very important in the future when we're dealing with things going up and down and left and right. And so we'll have to keep track of the directions there. Question 3 is going to be like just key. I mean, you should be able to know these like the back of your hand, and you don't want to be bogged down, especially when you get to the kinematics, about whether is this a velocity, is it an acceleration, is it what? So make sure you are familiar with these things. Okay. By the way, the key, if you didn't know, it's linked on the OneNote. It's mostly done. There's a lot of parts that aren't done, but that's okay. Just let me know if you absolutely want me to finish one, and I will finish it for you. But definitely check that out to see what you got right or what you got wrong. All right. So let's see, looking at the first part. See, I kind of combined these two because 1.1 and 1.2 because, well, as you notice, there's a lot of overlap. All right, let me just move my phone out of my way before I knock it over. Got my phone set up too, so if you message me over Remind, I'll see it. So a couple things. First of all, when it comes to displacement time graphs, distance time graphs, just keep in mind that you can do a couple things with it. Like here, for this question right here, these questions, you should be able to use the words to describe what the bug does. All right. Remember what the graph is showing you. In a distance time graph, it's another word for it is a position time graph. And what it's doing is it's literally just graphing. It's just showing you on a piece of paper what the object is doing or where it's at a specific time. So in this case, it's moving in a positive direction. It's moving, what we might say, away from the sensor, away from point 0. Here, it's not moving at all. It's just staying there. And here, it's moving in what we call a negative direction. Okay? And because, I was going to say, because the line is straight, we know it's a constant speed, a constant velocity. And here, I'll tell you what. There was a question up here. We go. Question 22. Be familiar with this. Okay, this is pretty much what it boils down to. What I was going to say. If you have a position time graph or a distance time graph, the speed at a given time, what do you do there? Well, you find the slope. Okay, you just find the slope of the line. And if you get a positive slope, it's moving in a positive direction. If you get a negative slope, it's moving in a negative direction. Okay. Where the object is at a given time. Well, you read the graph, okay? So, I don't know, I guess I'll just say read the graph, read it. You go over and up. So like, for example, no, that's not a good one. For the bug one, I mean, where is the bug at 10 seconds? Well, you go over to 10 seconds and you go up and you find out, well, the bug is 8 meters away, all right? So that's all you do. When it comes to direction at a given time, that kind of comes along with the slope. So it's either going to be a positive or negative slope, okay? Or negative slope. And if it's sloping upward, like I said, I mean, repeating myself now, but it's positive direction. If it's sloping downward, it's a negative direction. All right. That's pretty much all there is to that first section. The only thing I would say is, I'll mention it now and I'll mention it again later, is there's two things you want to look out for when we're talking about describing motion. You want to make sure that you know you can find its direction. Okay, so in the terms of a position time graph, if the slope is positive, then it's moving in the positive direction. If you get a negative slope, it's moving in the negative direction. And you can also tell if it's what's going on with its speed. Okay. Speed change, I'll just put, okay, that's a little triangle delta, that means change. If it's, what's it doing? So like, find the slope, I mean, that's the speed. You know that it's going a certain speed, basically what's going on. So direction and speed are the two things you want to focus on when you're talking about motion. The change in speed really comes into play when we're talking about velocity time graphs, but you should know the direction and the speed of it, all right? I don't know if that was clear or not, but if not, just send me a message. All right. Now, when it comes to, for example, question 23 and 24, graphing these, especially 23, make sure you know the general rules about graphing. You should have a title. All right. I'm going to get rid of this paper because it's getting in my way. You should have a title. You should have axis labels. Okay, I'm writing kind of sloppy because I hope this is a review for you. And that includes on the x-axis too, so label down here. And I'm totally just speeding through this because it's review. The numbers here should be evenly spaced out. In other words, you should go like 2s or 5s or 0.1s or 0.2s. Make sure you like evenly space them out. You scaled it correctly. All right, you should just be 0, 0, and the same thing on the y-axis. So you should do that. When you plot your points, you plot your points. I mean, here's the points up here. And once you do that, you use a straight edge to, as best you can, draw a trend line through the dots. Not connecting the dots, but through the dots. All right, so just be aware of the basic graphing rules. I think most of you are pretty good with that, but I wanted to mention it. All right, not seeing any questions yet, and that's okay. Maybe I'll answer the questions, especially since that was the slightly easier part, because then I turn this page and most of us just sort of feel slightly nauseated, maybe. Maybe not, because when it comes to velocity time graphs, it's very easy to overcomplicate it and to, I don't know, overcomplicate it. So, no, Siri, I wasn't talking to you. Sorry about that. How do I say this? The trick to these velocity time graphs is, again, just remembering a couple things. Is it moving positively or negatively, if at all? And is the speed changing? Is it speeding up, slowing down, or staying the same? All right, so when you see a graph like this one right here, describe the motion like in this graph. Well, first of all, you look at it and you got to realize there's three parts going on. There's three things going on here. You could draw a line like this and a line like this to sort of break it up into its three parts. And so don't take it all as a whole. Take it individually. And then you got to ask yourself the two questions. What direction is it moving? Direction. Okay. So in this case, because the velocity is, in this case, the velocities are negative, that means it's moving in the negative direction. You might say it's moving backwards. Okay. And then you got to ask yourself, is there a change in speed, or what is the change in speed? In this case, the speed, it's a flat line, so the speed is not changing. It's not increasing, it's not decreasing, it's just staying the same. All right, so there's no change in speed. And so in this case, it is moving backwards or negatively in the negative direction at a constant speed. That's what happens for the first part. For the second part, it's moving positively, positive direction at a constant speed. Okay, all the velocities are positive here. For the third part, all the velocities are still positive, but what's happening to the speed? Well, it's getting closer to zero. And as the speed or velocity gets closer to zero, that just means that it's slowing down. All right. So the key here is this. See if you could establish what direction it's moving and then what's going on with the speed. That's all. That's it. And then break it up into parts and just take your time with it. Okay. The same is true for position time graphs. So right next door to that is this little guy right here who looks kind of intimidating, but once again, break it up in two parts. Okay, we got this curvy piece right here. That's a part. And then it curves upward, and then it kind of changes again, and then we get this last part. All right, so three parts again. What's it doing? Well, the rules change slightly for reading a position time graph. I mean, you still want to find out what's the direction, what's the speed, but you have to look at it through a different, you got to look at it in a different way. Okay, now you got to look at slope. Okay, is going to be your determining factor for the speed. So in this case, it's sloping generally downward, which means it's, how do I say this? It's going backwards. It's got a negative velocity. So it's got a negative slope, which means it's got a negative velocity. All right. What's happening to it? Well, it's steeper at the beginning, which means it's going fast, and it's shallower at the end, which means it's slowing down. So steep slope means a high slope, which means a high speed. A shallow slope means low speed, shallow speed. So it's hard to kind of condense all this into one little live stream review, but you just got to break it down. In fact, it might be a really good idea to look at at those notes that went along with this, because it really breaks it down, like what's going on. All right. I'm not going to do this for all these, I think, but how do I say this? So when it comes to, I've got a blank sheet of paper right here. Okay, let's break this down then. For a position time graph, okay, and again, this is from the notes, but it's review time, right? So you can find the speed by finding slope. Okay, you can find the direction by positive or negative slope of the slope. I don't know, like, is it positive or negative? Basically, is the slope, how we write that? Is the slope positive or negative? Is slope plus or minus? Okay, so direction is either positive or negative, right? That's pretty much it. So then we move on to the velocity time graphs. Okay, so the speed, well, you just read it. Like, is it on a, what's the number of it? Like for example, this one, there's no number, but I do know like it's going a certain speed. I know it's going backwards. Okay, so the speed is basically read it, because it's a velocity time graph, so it's literally plotting velocity and time. When it comes to direction, well, for that you look at like, is it which quadrant? Is it positive or negative quadrant? So that's how we knew like this one was negative. It was moving backwards. It was moving in the negative direction because it's in the negative quadrant. This one's in the positive quadrant, so it's moving positively. All right. There's one more thing you can get from a velocity time graph that you can't necessarily very easily get from a position time graph, and that's acceleration. Oh, that is going to break. Okay. Acceleration is the slope. All right. And once again, you can either, is it going to be positive acceleration or negative acceleration based on, is it a positive slope or a negative slope? Okay. So you get not just a number, but you get if it's positive or negative. Whoop. We got a question. How do you represent a positive, a PT graph traveling in the negative direction? That is good. Let me, so good question, good question. Okay, I won't necessarily flash all those. So a position time graph traveling in a negative direction. So that goes back to this question. That's a perfect question. So I don't know when you sent that, but I will, I might have addressed it as you were, like there's a delay, so I might not have caught it, but yeah. So how do you know? Let me rewrite this a little bit clearly because I got some eraser marks. So how do you draw a position time graph representing something moving backwards? Well, like this, basically. It could go like that's moving backwards, moving in a negative direction because the slope is a negative slope. This would be also moving backwards, and this would also be moving in the negative direction. So all three of those are moving in negative direction because all those lines are trending downward. All right, great question, great question. So I will actually write this all moving in negative direction. All right, cool. So let me know if you have any other questions. But that basically, so to recap with velocity time, so again, PT, I'll come back to it because there is a 18-second delay here between me talking and you seeing this. So please let me know, I'll come back to this. Okay, so velocity time graph, like I said, you could do those three things with it. For the acceleration time graph, I mean, there's not a whole lot going on here. Just keep in mind that it's similar to the velocity time graph, except it's all about acceleration. So what is its acceleration? Well, you read it. Okay. So I would have, like, for example, this one right here. If there were numbers associated with it, you can read it and you can tell me what it is. What's the acceleration from here to here? Well, it's not changing. It's going to be the same acceleration. And then it goes negative here, and then it goes positive here. So that's basically what it's doing. So is it a positive or negative acceleration? Well, read it. Tell me. You tell me. So here it's a positive acceleration. Here it's a negative acceleration. And here it's a positive acceleration, but it's not accelerating as much as it was originally. All right. So on acceleration, that's a tricky one. And I told you a couple weeks ago, and you're starting to believe me maybe, that this is possibly one of the hardest concepts to understand, fully understand it. And it's because it doesn't go well with stuff that we think about. So, but here's basically it. So if you have a positive acceleration, okay. Remember I said think of acceleration as like the wind. So if you've got the wind blowing in a positive direction, what's it going to do to you? Well, if you're moving positive, then what's going to happen? Then you speed up. Okay, you get faster. But if you're moving backwards, if you're moving in a negative direction, then slow down. Oh, hey, let's see if I can write that where you can see it. So if you have a positive direction, that means the wind is blowing forward. It's blowing positively. And so if you're moving in that direction positively, you're going to speed up. It's going to speed you up. If you're moving in the backwards direction, negative direction, then that wind that's blowing positively is going to slow you down. So it's possible to have a positive acceleration, but it slows you down. Okay? So trying to think what that'd be. That would be like if you're in a car and you're moving backwards and you hit the brakes. Well, if you're driving backwards and you hit the brakes, what direction is the brakes pushing the car? The brakes are pushing the car in like the forward direction. And so, okay, so the car's moving backwards, the brakes has to slow it down by pushing forward. Or let's say there's a runaway car, like, right? So the car starts to roll backwards down a little hill. So what direction does everybody got to jump out and push it? Everybody's got to push it forward. Everybody's got to get in the back and push it forward. So that would be like a positive acceleration slowing the car down. All right, cool. So if you have a negative acceleration, then kind of the opposite is true. Then if you're moving positively, so the wind is now blowing you backwards, blowing in a backwards direction, negative direction, then what's going to happen if you're moving forward? Well, then you're going to slow down. Okay? If you're moving negatively, then you're going to speed up because you're moving backwards, the wind is blowing you backwards, so you're going to have a negative acceleration and you're going to increase your speed. Okay, it's like if you're in the car and you've got the reverse on and you hit the gas, what's going to happen? Well, the engine is pushing the car backwards, so you're going to speed up going backwards. All right. All right. Pardon my sloppy handwriting. I'm trying to go fast. Well, trying to balance and not to waste your time. All right, cool. So, let's see. I'm making sure that I'm checking everything I need to check off here. So, okay, talk about velocity, time graph, slope. Okay. Oh, area under the line for displacement. That, not that one. Let's see. Is it this one? Whoa. Can you show what moving positive and slowing down looks like and vice versa? Yes. Okay. So before I get to area under the line, okay, let's do, I kind of talked about a couple of these. Let's do all four really quick. So, boop. Moving positively and speeding up. Okay. I guess I'll just use the car as an example because why not? So you're in the car and you're moving forward and you hit the gas, the engine pushes you forward in the forward direction, so you're going to speed up. Okay? So moving positively, positive acceleration. Yeah, okay. Moving negatively and you have a positive acceleration, same idea, but now you're going back, you're moving negatively, so you're in the car, you're going backwards, all right? So you're driving backwards and then, I don't know, you're not going very fast, and what would stop a car besides the brakes? Oh, you're driving up a hill, and so gravity is trying to pull you back down the hill. So gravity is trying, like you're driving up the hill going backwards, and so gravity is trying to pull you forward. So if you were to if you're just rolling up a hill, what's going to happen? Gravity is going to pull you back down. So another way is you're moving backwards. You're hitting the gas and you're moving backwards, and you hit the brakes. The brakes have to push you forward to stop you. All right. Let's see. You're running backwards for whatever reason, and you like there's a giant wind that just kind of stops you from moving. Okay. So all those are examples of a positive acceleration when you would slow down. A negative acceleration and you'd slow down is when you're moving forward and the wind is blowing against you. So you're moving forward and the wind is blowing against you. You have a negative acceleration. So I guess now you can say you try to roll a ball up a hill. Okay, the ball is moving forward, but gravity is trying to pull it back down the hill. That would be a negative acceleration. Okay, if you consider going up the hill as positive, gravity is trying to pull it backwards. That's a negative acceleration. All right, so what's going to happen to the ball? It's going to slow down. If the ball goes far enough, then the ball is going to stop and it's going to start to come back down. Now the ball is moving backwards down the hill. Gravity is pulling it backward down the hill. Negative acceleration. The ball is moving backwards, so it's going to speed up going back down the hill. All right. If that doesn't help any, let me know. All right, I can answer the more questions about that now or tomorrow in class. Either one. All right. That was a question on the Remind app, so that was a good question too. All right. So I'm going to put up my answer key because, I'll start it without it. Let me get this paper out of the way here. Okay, so we have a velocity time graph. I could center things. All right, we have a velocity time graph. And I think most of you could probably, what's the velocity? Well, you read it, okay? What's the velocity? It's a velocity time graph. You just read the graph, all right? What's the velocity again? You just read it. What's the acceleration? So I'm going to put read it. You could look up the answer on the answer key. Okay, so read it for velocity. It's a velocity time graph. For acceleration, what do? Well, it's a velocity time graph. You find slope, okay, for acceleration, for those ones. Now, for finding slope on things like this, I'm going to tell you. It says at 25 seconds. That's not a good one. 45 seconds. That's a better example. So at 45 seconds, this line is smack dab in the middle of this little segment here. And on a pre-printed out thing like this, where it looks like it's meant to be like the line goes from here to here, use those as your endpoints when you're finding slope. All right. One equation you might want to include on your note card, it is on the equation sheet, but it's the slope equation where y2 minus y1 over x2 minus x1, x2 over x1. Write it down. Know it. What points do you use? What points do you use? You just use the endpoints of that line. All right. So it says 45. I could have asked, what's the acceleration at E? Well, at E is right here-ish, kind of. So it's unchanging. So find the slope of that entire line. All right. That's just a handy little tip. Makes life a little bit easier. All right. Okay. Blah, 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 blah. What's object displacement? By the way, if I blah, 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 blah through something and you need to know the answer to it, let me know. The object's displacement between 0 and 10 seconds. This is where you find the area under the line. Okay, so between 0 and 10, you want from here to here. And so that means the area under the line is going to be all this. Okay, that is a triangle. And so you want to find that area of that triangle. And so you just do, which one was this? This is number 36. The area of a triangle is 1/2 times the base times the height. So you literally just say 1/2 times 10 seconds times the height, and it goes up to, looks like 150. Multiply that together, you got your area, and you find your displacement. The units cancel out, so that seconds is gone, and you're left just with the meters, the distance. All right. On the key, I have all that answered. How am I doing on time? Getting kind of ripe here, 27 minutes. So on the key, I have all that worked out for you if you want to check it out. All right. You could also ask me tomorrow in class if you want. Okay. I haven't even started kinematics, so I think that's about it for the graphs. All right. Just go back and look at the graphs, look at the quiz, see how you did. All right. Look for things that you might have mistaken. How would you find the average speed of a car? Oh, now we're getting out of this. Okay. So I kind of talked about that. I should probably put this over here so I could see it. Okay. Okay, explain the following. Okay, so 41 is kind of like what I was explaining, so I already gave some examples. I'm going to skip that. Kinematics. All right, so Kinematics. Took a quiz today. I don't know how you did. Well, I know how you did, but I don't know how you did, because I don't know. You know how you did. So check it out. Make sure you go back and see how you did and look at the ones you missed. Okay. Really, you want to have these handy, these equations handy. I'm going to give you the equation sheet, but most importantly, you should be able to identify distance, acceleration, time, all that stuff, like at the drop of a hat. Like no problem at all. Okay. There's one question I know that you guys want me probably to do, and it's one like the number 47 here. So I'm going to work it out, and I'm going to be kind of brief because I don't want, I want you guys to have an evening. So Rod went away from Todd, and these are called catch-up questions, and they're meant to be like more problem solving and puzzle solving than like, here's the formula on how you solve catch-up questions. Okay, because that's not what we're going for. However, this is basically how you do it. So the thing is, when you have a situation like this, you want to pick out their speed. So it runs at 2.4 meters per second. Who does? Well, Rod does. So Rod's velocity is 2.4 meters per second. Okay. Todd chases him at 4.3 meters per second. So I'm just going to say, well, Todd's velocity is 4.3 meters per second. And so I've got two velocities. It's not initial and final. It's just two different people or two different objects. It says Todd chases Rod, and it gives, after giving him a 6.4 seconds head start. So think about who left first. Who left first? You're going to want to write their time first. So they ran for different amounts of time. So Todd chases Rod after giving him a head start. So that means Rod left first. And since he left first, he's going to have his time, the time that he ran for, will be whatever Todd's time is plus the 6.4 seconds. All right. If you get that far, you're in pretty good shape. Okay. After that, I'm going to kind of fudge this a little bit because I ran out of room, but you got to realize that the distance that Rod travels will be the distance that Todd travels. Okay. I wish I could put up some fancy graphic on the screen, but I can't. So basically one leaves sooner, the other one starts to catch up after a second. That was horrible, but that's what's going on here. And so the distance that they run is the same. And so just to kind of like, distance is velocity times time, so that's just sort of something that we keep in mind. That's the first equation. We can, instead of saying that Rod's distance is equal to Todd's distance, which is not super helpful to us because we don't know how fast they ran, we could say, well, Rod's velocity times Rod's time is equal to Todd's velocity times Todd's time. All right, and then we go from there. That's the hardest part, I think, is getting to that point, because I think once you get to that point, it's just plugging in numbers and solving for it. Okay, so really focus on understanding what I just showed you, and I'm going to go through it really quick again. You separate out, like, it's not an acceleration problem. There's not a starting and a stopping point. Okay, like it's not like somebody speeds up to catch to it. They're just constant speed. Everything's constant speed. This is average of velocity. So there's basically three-ish types of questions. You're going to have the type of questions where you have a constant velocity, which is just velocity equals distance over time. And then the sort of subcategory of those is what I'm doing right now, all right, where there's no acceleration involved. Then you're going to have questions that involve an acceleration, and that's sort of like a whole separate thing. All right, that's what we worked on 2 days ago. Okay, so keep that in mind. There's sort of 2-3-ish types of questions you're going to see. All right, now to finish this up, I'm not seeing any questions, but there's an 18-second delay, so I guess I'm going to put a line here. This kind of blurs the thing a little bit. So velocity of Rod is 2.4 meters per second times Todd's velocity. Times Rod's time. Make sure I'm on the screen here. So Rod's time is this 0.4 seconds. All right, so I'm just plugging in what I got from over on the left, and that's equal to Todd's velocity, which is 4.3 meters per second, times, well, we don't know his, so Todd's time. Well, this is hard to say out loud. So now I've got this equation to solve. And like I said in class, this is very, 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 very similar to something like if you had 2.4 times x plus 6.4 is equal to, 4.3, 3 times x. I kind of screwed that up a little bit, but a lot, okay? If you could solve for x, you're good. And that's essentially what we're doing, okay? It's just that there's units involved now, and it's not x, it's a named variable. So that's exactly what I'm going to do right now, and I'm going to get out my handy dandy calculator and start calculating some things. So I don't need to do this one, so I'm going to say 2.4 meters per second. I'm just going to distribute this times Todd's time plus 2.4 times 6.4, 15.36 meters per second. All right. Oh, can you do number 60? Yes, I will. Definitely. 62. All right. As soon as I get done with this one, is equal to, and there's nothing to do here, 4.3 meters per second. There's nothing to distribute here, times Todd's time. Okay. So then basically I have to subtract, let's see, I'm going to subtract 2.4 meters per second times Todd's time from both sides. So I'm going to get 4 minus 2.4, and I'm going to get, let's see, 15.36 meters per second. By the way, I'm rushing through this one, but if you want to see me do another one slower, I have a whole video on that, so you can watch that one only. It might even be the same question, but I don't know, it'll be similar. Is equal to 1.9 meters per second times Todd's time. Okay, so now I've got to just divide. So I'm going to divide both sides by 1.9. So 15.36 divided by 1.9, and now I have solved. This is kind of getting tight here. Todd's time is equal to 8.1 seconds. And now you see why I have you put boxes around your final answer. So that's how fast, that's how long Todd ran before he caught up with Rod. So that's that in a nutshell, like literally the speedy version of that. But like I said, there's a whole video on it, but I just want to run through it one more time. This part at the beginning is your key. So distance first, constant velocity questions, velocity is distance over time. There's a little subgroup of questions, the catch-up questions like this, and then we get into the acceleration questions, okay, where the velocity changes. All right. Let me see what 62 is. So I got a request for that. Yes, good one. Okay, some questions are going to be like, let me just double check. Make sure you do it. Okay. Some questions are going to be, you're going to see some situations, some questions that are going to be like number, and I'm going to get to 62, but some are going to be like 49. All right. So, and 50 and a whole bunch of the other ones where it gives you a initial velocity. So initial velocity, and they slam on their brakes. And it tells you that they stop. So you have a VI and a VF. All right. Gravity has nothing to do with it. It's just VI, VF. It tells you a time. Where does the time go? Blah, blah, blah. Oh, there it is. So here's your time, 1.3 seconds. And in that case, what's its acceleration? Very straightforward. You would probably, unless I'm missing something, I think you would probably use this first equation, because you have VF, you have time, you have VI. You just have to solve for acceleration. All right. So you'll have questions like that. Those are straight up acceleration questions. So that's the third kind of questions I was talking about, where you have something that is going a certain speed and then it's going another speed. All right. It's the same object, two different points in time, different speeds. That's when you're going to start using acceleration. All right. So it wants to know acceleration. So I just want to be clear on that. these are different than some of the other questions that are above, and you gotta be able to recognize them. I know they're kind of separated here. All right. And could you also do number 6? Oh yes, okay. So I think you guys, what you really want to see is, yes, acceleration due to gravity. All right, now you have to sort of have your 62, okay. So I'm gonna do 62 and 66, okay. You gotta be watching out for these. Now, on the review guide, they're sort of chunked together, and so you kind of get clued off in that way, but you gotta watch out because things like in 62, question 62, all it tells you is that it rolls off a cliff that's 10 meters high. So like, what is that? That's distance very clearly, but then it's asking how long is it gonna take to hit the bottom, all right? How long is it gonna take is a time. That's a time. And that's all it seems to give you. But you got to watch out for some key words here. It rolled off a cliff. Okay, rolled off. That tells you right there that nobody was throwing it. It was like just passively rolled off. So that's going to tell you that VI, the initial velocity, is 0. Okay, so look out for key words like that. You're going to see words like dropped. Okay, I know that's not a question to solve, but you're going to see words like that where things were just released, or they were dropped, or they just were let go. And you'll see other questions where it's like it was thrown down at an initial velocity of blah blah blah. And so you got to watch out for those types of questions. So that right there is a clue. Okay, and when you have something falling, you just got to remember, I'm going to write, if something is falling, then that's terrible. Then the acceleration is, I'm going to say 9.8. Okay. And I know you might be wondering, what about that negative 9.8? Okay, what's the point of the negative? I'm just going to take a little side rabbit trail right here. What's the point of the negative? The point of a negative is to show direction. So I'm going to just say negative sign shows direction. Okay, and to simplify things for now, let's not worry about the direction of it. We're going to assume everything is downward. Okay, so we're going to just kind of stick, because if we did negative 9.8, then we got to make sure we did a negative 10 meters because it's falling negative 10 meters. There's nothing wrong with that. In fact, I encourage you to do that, but just for clarity's purposes, just for setting this up, maybe it's a bad habit, so maybe I need to rethink that, but I just want to point out these two main things. Rolls off VI 0, and it's falling, gravity then, okay? So gravity. Alrighty. So how do we do it? Well, VI is equal to 0. The distance is 10, and a big part of me wants to write negative 10, but I'm just going to leave it at 10. We know acceleration is 9.8 meters per second squared, and we want to know the distance, right? So I don't have my equation sheet on me, but I do have them all written down. We've got VI. So we gotta look for what we're trying to find. We're trying to find distance. So maybe I'll check this one right now. Distance, yep, well, we're trying to find it. Acceleration, 9.8. The time, do we? We don't. Wait, we're not trying to find acceleration. We're trying to find time. So we've got distance. Oh, wait, let's stick to this magic one here. We got time, we're trying to find time. Do we know the distance? Yes, 10 meters. Do we know acceleration? Yes, 9.8. Is velocity initial 0? Yes. Good. Otherwise, we would have to use this one. So that's how you do it. You just get your checklist. This is why I have you write down all these parts, so that you can tell kind of a little bit easier which equation you're going to use. So it's 2 times distance divided by acceleration. And since initial velocity is 0, we can use it. We plug in our numbers there. So 2 times, I guess I'll finish this out really quick, equals 2 times the distance, 10 meters divided by 9.8 meters per second squared. And basically, when I plug it in my calculator, well, I guess I'll do it really quick because I don't have the answer ahead of me or in front of me. So it's going to be 2 times 10 divided by 9.8, and I get 1.4. So the answer is letter B. All right. 1.4 seconds. But excuse me, those clues, look out for the clues. Okay, something like rolling off 0. If it's falling, then gravity is going to be involved 9.8. All right. Let me know if you need clarification on that. I will definitely help you out. I think I'm going to finish it off after this one. So this one, you throw a ball straight up. Okay, what is the magnitude of acceleration at the top of the rise? So I think it was yesterday. The opening question was this exact question. So I'm going to answer that kind of a longer way. So we have a ball. Okay, it's thrown up. I'm going to arc it because it's easier, and it's going to get up to the top, and it's going to come back down. Okay, so it gets thrown straight up, and it comes basically straight down. Okay, so there's two things to keep in mind. First of all, question 66 is asking about what's its acceleration at the top of the rise. Well, what's causing the ball to slow down when it goes up? What's causing the ball to speed back up when it goes down? Well, it's gravity, right? Gravity is causing the acceleration. So the acceleration is going to be, well, is it 9.8? I didn't use negative here. All right, so for simplicity's sake, because once again, the negative just indicates the direction, the acceleration is going to be 9.8 meters per second squared. So to answer the question for number 66, there you go. Okay, gravity is always pulling. It never shuts off. Okay, now the question might be, because you saw it on the quiz today, what's its velocity at the very top? And in that case, the velocity is going to be equal to 0, because it has, you throw it up in the air, it slows down, and it stops briefly, not briefly, like instantaneously, and then it starts to come back downward. It gets really slow at first, faster. Okay, so be careful what the question's asking. It was on the quiz. There was a question like that on the quiz today. There may or may not be a question like that on the test tomorrow. There'll be maybe something similar, but I think the point is, can you identify that gravity is always pulling downward and it's causing an acceleration of 9.8 meters per second squared? All right. So question 67 gets to the direction part of it. Okay. What else? I think that's about it. That's it. Okay, so when it comes down to it, the kinematics part, like I said, there's three types of questions. Like the constant velocity, distances, or velocity is distance over time. You got the little kind of similar stuff, or at least the related stuff with the catch-up problems, and then you have the acceleration questions. Some of those involve gravity, some don't. If something's falling, it involves gravity. All right, look out for here. Actually, I'll write this down. I'm gonna write it. I'm gonna write it back up here. No, I'm gonna write it down here where I have some room. Look for, is there a VI or VF? Okay, that's the first thing you want to do. Is there initial velocity or final velocity? If no, then it's probably just a constant velocity question. Okay, but if it seems like something's speeding up or slowing down, then ask yourself, which one, if any, is 0? All right, so look for the clues. Something slowed to a stop, something started from rest, something whatever. Like, look for clues to see if it's if one of those is 0. And then finally, is gravity involved? I'm getting tired. That says involved. If so, if yes, then, oh boy, I'm running out of room. Acceleration is 9.8 meters per second squared. Okay, so seriously though, like if gravity is involved, then acceleration is going to be negative 9.8. It's going to be 9.8 meters per second squared downward. All right. Oh, number 64. I got a request. Yes. Ha, good question. Okay. So number 64. Oh, wait, is there a 64? There it is. Okay. You throw a ball straight up at 14 meters per second. There's no air resistance. How fast is the ball traveling when it returns to you? That's a good question. And if you look back to our little example over here, what's happening? Well, let's say you throw the ball up at 14 meters per second. So 14 meters per second up. Okay. So think about this, and it's going to make total sense to you. And probably you already kind of know the answer, but what's going to happen? Well, it's going to go up, 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 and it's going to get to, so it starts at velocity is 14 meters per second. It's going to get to the top. It's going to be 0, right? So then it's going to fall, and it's going to fall the exact same distance downward, and there's no air resistance to slow it down or anything like that. And so what's going to be going on when it comes back down to the exact same spot that it just fell from? Well, it's going to be going 14 meters per second downward. All right, so hopefully that's choice C, I think it is. All right, so it's basically like somebody stretched out a rubber band. You pull out the rubber band, and then you let it go. It's going to go right back to where it started from. All right, assuming there's no resistance or anything like that. Okay, so I think that's good enough. Tomorrow, 50 minutes, 49 minutes. It's not bad. I'm going to try to stall a little bit in case somebody wants to ask for another one, but I think I basically covered it all. And tomorrow in class, we'll work on our note card. I'll answer any other questions you might have. I don't think I'm going to do a whole class thing since I'm doing that now. And yeah, that's basically it. Okay. So unless there's any last questions in the next couple seconds, I think I'm going to call it. So a couple last minute tips. Look back over those quizzes, and look for the little hints that the little tricks and tips I was giving you throughout, like this one I wrote in purple and this one I wrote in green. Okay, look for things like that and just kind of remember them. Maybe mark them on your note card or something. All right, so you'll be good, and I'll be in tomorrow freshman hour. And whatever you need. So, all right, I think that's about it. I'm not seeing any other questions, so you guys can do this. Just study it, look it over, and you can remind me. You can use the Remind app if you have any questions. All right. Well, have a good night. See you tomorrow.